Okay, quick mic check. Can everyone hear me?
Yes, I can hear you.
Awesome, thank you. Okay, just a quick check. Is this where we left off? Did we cover this already?
Yes, you did.
Okay. And did we talk about the delta G or Gibbs free energy in detail? Or did we not get to this yet?
No, you were going to do this today.
Okay. So we'll get started with this and give it another minute, then we'll get started. Okay, so using our equation here, right, we can actually determine whether something is going to be spontaneous or not. Our goal is to get delta G to be negative. So whether or not it's going to be spontaneous dependent on what these symbols are for my delta H and my delta S. So some combination of this will generate a negative charge for this, whether it is going to be spontaneous or non-spontaneous, and also dependent on the temperatures. So the two main ones that we're going to look at right now are delta H is negative. So this combination, and then delta S is positive. So for this combination, no matter what the temperature is, it will always be spontaneous. Okay. So the reason why this works, if I mathematically apply it in, this is always going to be a positive value, this is going to be a negative. So this is a negative minus a positive, so it makes it more negative. But this is always going to be negative no matter what number I have. Any questions so far? Okay. Now the opposite is true if this was positive and this was negative. When that happens, my positive is subtracted by a negative. It's always going to be a positive number. That's why this one is always going to be non-spontaneous no matter what temperature I give. And remember, our temperature here is in Kelvin. So I can't have a negative Kelvin. The lowest Kelvin temperature I can have is 0. Okay, any questions before we move forward? Okay. Just a reminder to people who are co-hosts to please go ahead and click the record button. Now, the other two scenarios are whether when they are both positive or both negative. So the example I have here, if delta H was positive and delta S was also positive, I have a positive minus a positive. Okay. And then I have temperature over here. So this is how the two things are related. Now, my goal is I want delta G to be negative. So the best way to get that is I want the second value here to be bigger than the first value. So I want this to be larger. And the only way I can make this larger is by increasing my temperature. So at higher temperatures, my overall value of T delta S is going to be larger than my delta H, making it negative. So as long as we have an increase in temperature, if we get a very high temperature, it should be spontaneous. Any questions so far? Okay, the opposite is true if they were both negative. So I have a negative minus a negative. This is my T over here. I want this value right here to be very small because a negative minus a negative means it's a positive. So I want this value here to be very small so that this negative stays negative. With that said, temperature should be a very low temperature. And the more lower we go with the temperature, the more likely it will be spontaneous. Okay, any questions up to this part? All right. So if you were confused about all of that, here is a good summary of it. Depending on the symbol of your delta H and your delta S, it can also refer to the symbol of T delta S as overall. This will help you determine whether or not your delta G is going to be spontaneous or not. So the first two that you see are up here. If delta H was negative, delta S was positive is always spontaneous, no matter the temperature. If delta H was positive, delta S was negative, it's never spontaneous, no matter what temperature you have. If they're both positive, you want a higher temperature to be spontaneous. If they're both negative, you want a lower temperature. Okay. Anyone have any questions? All right. So go ahead and take a minute using the information that you see here. Tell me if this reaction is going to be spontaneous at one of these 4 possibilities. Okay. Okay. Who still needs more time for this problem? Okay. Who doesn't understand how to start it? Okay. I want you to look at this picture right here. If you had to guess what phase this is, what phase would this possibly be? the picture on the left. Okay, so we have a gas phase. Take a guess as to what the picture is on the right side. What
Is it
phase?
the liquid phase?
It is the liquid phase. Solids are more organized. Okay, but this kind of fits in either scenario. It still works. So in order to go from a gas to a liquid, am I losing heat or gaining heat?
Aren't you losing heat?
You're losing heat, right? So this is exothermic. You are releasing heat. Okay. What did that tell me about delta H?
That the delta H is positive?
Negative.
Oh,
When you lose
Oh.
heat, delta H is negative. Okay. Now
oh,
let's
I
take a
had
look
it
at
the wrong
the
way around. Okay, thank you.
let's take a look at the scenario here. If I'm looking at this picture here, I have gas changing into a liquid. What is happening to my delta S? Am I getting more disorder or less disorder? It is lower entropy, so it is negative. Okay. So there's less disorder, so it's more ordered. So I know the sign of this and this now. They're both negative. How would I guarantee that this is going to be a spontaneous reaction? What condition do I need in terms of temperature? I need lower temperature. Okay. If the temperature starts increasing, then essentially it could be non-spontaneous. So the lower the temperature, more likely it will be spontaneous. Okay. Anyone have any questions on this one? All right. So just as we mentioned before, delta S and delta H are both negative. Spontaneous means that it happens or occurs without excess input of energy. Delta H is the heat of enthalpy or change of enthalpy, the heat measurement. If it's negative, that means we're releasing heat. If it's positive, we're gaining heat. Okay. Any other questions? All right. So this is very similar to what we did before, but this time I want you to actually go ahead and calculate using numbers that you have. So you're given this information right here. Go ahead and determine if this reaction is spontaneous at this temperature, and then what happens as I increase the temperature over time. Okay. Then another scenario is this reaction spontaneous at this new temperature here? And then find the new delta G value at this new temperature. Okay, I'll give you some time to get started with it, and then we'll go over it. Okay, so by now everyone should have figured out part A. And I understand you haven't gotten to part B yet because you need to do some calculations, but part A is pretty straightforward. So looking at this information, is this reaction spontaneous? Yes or no at 25 degrees Celsius? How do we know that? Delta G is negative. So it's already listed here. We see that answer. We don't have to do anything else with it. It's already telling us that this is spontaneous at 25 degrees Celsius. Remember, if you were to convert this in terms of calculations, you need to change this into 298 Kelvin because you need to do calculations with that. Okay. With that said, what will happen to delta G as we increase in temperature? delta H is negative, delta S is negative. As I increase in temperature, what happens to my delta G value? It becomes more positive. Okay. So once again, delta G starts to become more positive once we increase in temperature. Because in this scenario, we want a lower temperature in order for this to stay as spontaneous. Okay. With that said, I want you to go ahead using the same values that you have here, right? So we're not changing the values of delta H and delta S. We are increasing the temperature. We're changing to a new temperature with this. Calculate delta G at this temperature for me. So plug into the equation and calculate delta G for me. Okay, what did everyone get as an answer for delta G? And is it spontaneous or non-spontaneous? Or if you don't know how to do that, is anyone having trouble solving for this one? Okay, I see different answers so far. Let me go ahead and explain what you need to do first. This is in degrees Celsius. What do you have to change this to? You have to change it to Kelvin, okay? Once you get that into Kelvin, then we can plug into our equation. So this is in kilojoules, right? And then we have our temperature here, which comes out to 1173 Kelvin times, if you look at this value, this is in joules. So I need to either change this into kilojoules or change this into joules, one or the other. Okay. So if I change that, I need to go ahead and make this essentially 0.187, negative 0.1879 kilojoules. Then I go ahead and plug it in and solve for my equation. Okay, I'll just show you the answer on the next slide. Same exact thing, we plug everything in. Everything here happens to be in kilojoules, so they're the same units, and this must be in Kelvin. Your answer comes out to about 22 kilojoules, and because it is positive, it is considered non-spontaneous. So once again, the more positive it becomes, if it's both for a delta H that's negative, delta S that's negative, the more the higher the temperature, the more positive our delta G will become. Okay, any questions up to this part?
Yeah, Professor, I just had a quick question.
Sure.
So whenever it says for actually I see it there, it says that convert it to Kelvin. Is this always the case with this specific formula? You have to convert it to Kelvin?
Yes.
Okay, thank you.
Anytime you're dealing with chemistry, I would say 99% of the time, work with Kelvin. Because you want to avoid things such as 0 degrees Celsius. That's not going to help you. It's going to make something 0, which is not going to be beneficial. You want to avoid things such as negatives for Celsius. So same thing. You want to avoid all of these scenarios. Best way to do that is changing everything in Kelvin. The lowest temperature that Kelvin can be is 0, and then it just goes in a positive direction. Everything else in any other scenario. Does that make sense?
Yep, thank
Okay.
you.
All right. So this is just a summary of our relationship between T delta H over delta S. You don't need to know so much about this. If you remember those 4 possibilities that we have, this is just the same exact thing, but in a graph form. Okay. So the next thing I want to talk about is, well, starting from here, most of our stuff was concept heavy, with the exception of talking about delta G. Starting from here, we're relating delta G back to equilibrium. So everything always goes back to equilibrium. So we're going to look at the relationship between Q and K. If Q was equal to K in this scenario here, that means at equilibrium, delta G comes out to exactly 0. Okay. And in most cases, when Q is less than K, that means the reaction is going to shift to the right. That means I'm driving the reaction forward. It will move to the right on its own, which also means delta G is negative. So it is a spontaneous reaction. When we determine if something is spontaneous versus non-spontaneous, if it is spontaneous, it tends to drive the reaction forward in the forward direction to the right. So in our scenario here, this happens to go forward and to the right. And so that means the opposite is true if we're going in the backwards direction, moving to the left, then delta G is positive, in other words, it is non-spontaneous. It doesn't like to move to the right, it likes to move to the left. Any questions about this? Okay. So we can actually produce an equation using this information. We go ahead and write in that our delta G is equal to your RT ln Q over K, which can be broken down. If you remember that ln of A over B is the same as ln of A minus ln of B. Okay. So that's how we got the equation on the right side here. All right. Any questions so far about this? Okay. With that said, delta G has a very, very unique property here. If the number, so not necessarily positive or negative, we already determined which one was negative or positive, right? So when Q is less than K, delta G is going to be negative. When Q is greater than K, delta G is going to be positive. So that much is done. We know the symbol of it. The value of this of delta G, so the difference in the free energy, right, is if this number is very, very large, that means the difference between Q and K are very, very different. So Q would be something like 1 and K would be something like 10,000. Then my delta G value is going to be something in the maybe 3-digit or 4-digit kilojoules. So something very, very large in terms of number. If I look at my Q and K and the numbers are very close, an example I can give you would be like 4 and like 4.3, then these numbers are essentially very close to each other, right? That means my delta G value, whether it's positive or negative, is a very, very small numeric number, maybe something like 0.8 kilojoules, for example. Anyone have any questions? Once again, it's important to know this information right here. Delta G tells us two different things at once. Whether we have a bigger Q or a bigger K, and then how much of a difference they have. Are they very, very far apart or are they very, very close? That's what the symbol of delta G, the symbol and the number of delta G tells us. Okay, any questions before we continue? All right. So remember we mentioned this thing called standard state, right? And remember that standard state means 1 ATM, 1 molar concentration, and a bunch of other things. If I assume that I have either 1 molar concentrations or 1 ATM, then I can assume that my Q, which is my product over reactants, this is all 1 over 1, should give me 1. So my Q is equal to 1 at standard state. If Q is equal to 1, anytime you enter ln of 1, this thing becomes 0. So I'm going to go back to a previous slide real quick. If you look here, this is RT ln of Q. If this Q is equal to 1, this entire thing becomes 0. So when I write something that's called standard state, I simply put a 0 here to indicate that this is at standard state. If this is at standard state, Q is equal to 1. When I plug it into this equation, this becomes 0. Then all that is left over is just negative RT ln K. Any questions? Okay. So once again, with that said, we can also look at the relationship between delta G at standard state and the relationship with K. So as delta G at standard state becomes more positive, K becomes a smaller number. The opposite is true when this becomes more negative. This becomes a larger number. Anyone have any questions so far? Okay. So let's continue. We also have one final equation that we're going to work with, and this is combining all of them together. So we said that delta G here at standard state is the same thing as if I wrote negative RT ln K. Okay, so this is essentially the same thing. This is that. And that is why it's over here. So I'm essentially just writing the same equation that I had before. This is just RT ln Q minus RT ln K. But instead of writing this in, I'm changing this entire thing into delta G at standard state. So I'm just replacing it and then putting them together. Okay, any questions? All right. So we can see here the relation between delta G at standard state and K. It's not important to memorize this graph as long as you knew the information of which one's increasing, which one's decreasing based on whether it's getting positive or negative. Okay. So I'll give you a minute with this one. What I want you to do first is, if you look at all this information, it says that the mixture 1 is at equilibrium. Okay. Using that information, I want you to calculate our equilibrium constant. And this is these are the concentrations of each one. This is your green, this is your black, and you have 0.10 atm for each one of these molecules. You're also given your delta G at standard state, and this is the equation given to you. Okay, your job is to tell me which one of these mixtures has the most negative delta G and which one has the most positive. So you can essentially calculate each of these numbers and then determining which one's positive, which one's negative. Just out of curiosity, does anyone know what to do with this one? Or do you want me to go through it? You do use a standard state formula, yes. Okay, I'll give you some time to look over it, see if you can figure it out first, and then we'll go over it. Okay, so let's get started with the first one. It says that the mixture 1 in the first picture is at equilibrium. So we're going to go ahead and look at how many of these individual dots we have, and then we're going to put these into our equilibrium expression. So first things first, set up my equation here, and it's always product over reactants. And since this is a 2 here, this becomes my exponent. I plug in my numbers. In this case, they're telling me that there's 4 of them there. That's why it is 0.4. Remember, each one of these is 0.1. So each one of those molecules is 0.1. There happens to be 4 of them, so that's 0.4 over 0.2 over 0.2. My overall comes out to 4.0. So my K is 4.0. And once again, my equilibrium expression is set up the same exact way here. Any questions on the first one? Okay. With that said, I now have my value of K, right? I have different conditions to meet for Q, different mixtures and pictures, okay? And then I also have my information on my delta G at standard state. So that's given to me. The only thing I'm missing now is temperature. So I'm going to use some time to go ahead and find the temperature. I plug everything in. Algebraically, I solve for this temperature. The only thing I am missing in here. I have this, I have that, and I have that. I plug it in, I get the temperature to come out to be 295 Kelvin. Any questions on this? Okay. With that said, we're going to go ahead and take that number and plug it in now. For our very first mixture, we know this is at equilibrium. So I know that delta G is going to be equal to 0. Remember, not delta G at standard state, delta G itself. So delta G itself is going to be equal to 0. So this is 0 right here. Okay. We also know what this value is, and we do know what ln of Q is, because Q we can plug in and solve for. It happens to be 4 exactly the same way. So it's just ln of 4. Plug everything in. It should give me a value of 0. So this is going to be negative 3.4 kilojoules. This is also going to come out to about 3.4 kilojoules. 3.4 kilojoules. This is the negative. This is the positive. Any questions on the first one? Okay. With that said, we're going to go ahead and take a look at mixture number 2. So mixture number 2, I need to figure out what my Q value is. So I have to count how many of those molecules I have in each scenario. I get 0.44. Right away, I know Q is less than K. Okay. So I know that my answer here for delta G is going to be negative automatically. Okay. Any questions so far up to this part? Now we just have to plug everything in. We know this value here. We know this. We know this. We plug in our ln Q and we get our new delta G value. And it comes out to negative 5.4 times 10 to the 3 joules. All right. Any questions? For the person who messaged me about that, only I can suggest is to rejoin. Usually the best way of solving it. Okay. Now on to mixture number 3, same thing. You find your Q value. This tells me that Q happens to be greater than K. So this I know is already going to give me a delta G that is a positive value. All right. With that said, I plug everything in. My delta G comes out to a positive value, comes out to the positive 5.4 times 10 to the 3 joules. Okay, and we can determine that mixture 2 was the most negative, it is spontaneous. Mixture 3 was the most positive, is non-spontaneous. And then mixture 1 was at equilibrium, so delta G is equal to 0. So to find the value of K, we already determined it from the very first one. We plugged in our products over reactants. So I had some amount here, some amount there, some amount here, and some amount here. Okay, I believe that the number was 0.4 here, and it was squared. And then this was 0.2 or something like that. Okay. Does that answer your question? Okay. Okay. With that said, does anyone need time to copy this down before we move forward to the last part? Okay. For the last part, when we look at part C, it says that we are at standard conditions. So delta G is equal to delta G at standard state, which gives me this value right here, which tells me that Q is equal to 1. Okay. If I plug this into my equation, I don't even have to do the whole equation because this essentially just tells me that the delta G itself is equal to delta G at standard state. And since this is already a negative, this is spontaneous. Okay, any questions? All right. So in an effort to save time, why don't I go through this problem with you? We'll just go through it together and then we can move forward from there, okay? Based on this problem right here, we say that we're running this equation at a very high temperature. This is my equation. I'm going to go ahead and calculate the actual K value. And you're given this delta G value, okay? So really quickly, what equation would I be using to solve for my K given this delta G as standard state? Okay, I guess nobody knows. So you would go ahead and use your delta G at standard state is equal to negative RT ln K. All I'm doing at this point is just finding my K, algebraically solving for everything else. So I know the temperature that I have, 298, so I have that information. I know this, and my delta G is also listed right here. So I can plug these in and solve for it, and then we can go ahead and do the same thing because we have this information here. So it should give me the same value because the K should be a constant. So no matter which one I use, this information down here or the information up here, I should get that same K value. It's easier to use the first number because it's going to be smaller. Okay. So with that said, I plug it in. I go ahead and algebraically move everything around, get K by itself. I end up with a value that is pretty large. In fact, if you enter this into your calculator, this probably will not show up. The most you'll probably get is this. And that's okay. If you wanted to leave it at that, that is considered an answer as well. Okay. Any questions? Okay. So we'll do the same thing. This time when we go ahead and raise the temperature, our new K value is a little bit different. If you remember what was my original value of Q? Oh, sorry, we didn't do that part yet. I realized my mistake. I realized we didn't talk about the value of Q yet. So we're going to go ahead and talk about that in this category here. Okay. For now, all we did was calculate the values of K at different temperatures, 298 and 973. R is 8.3145 joules per Kelvin. Anytime we're dealing with energy, it is 8.3145 joules per Kelvin. Anytime we're dealing with pressure of gases, it is 0.0821 liters ATM over moles Kelvin. It's a constant, yes. Okay, so let's continue. We have the two K values, we've already determined them. The first one is a very, very large number here. And then the second one right here came out to about 4.5. I want you to remember those numbers, okay? The next thing I'm going to talk about is this problem right here. We are essentially figuring out Q. That's what the second part of the question is, okay? Then we're going to use that information to calculate the delta G because we have Q and we have the K. Any questions before we begin? Okay. So with that said, I plug this all in, I get my K value. It is a very large number. In the calculator, all you need to do is enter this. You don't need to enter that. This probably won't show up on your calculator anyways, okay? And the next one here is a very small number. So either one of these will give you the information you need. Now after that, we are calculating the value of Q. Q comes out to 4.0 for this scenario here. And now I want you to pay attention to this. One of my Q values, right? Oh, my Q is 4. I determined that my K values here, this was, I believe it was 7 times 10 to the 24, and this one was 4.5. Okay. Based on what you see here, which one is closer to the Q? The first one, right? This is actually the one at 973, and this is the one at 298 Kelvin, okay? So knowing that, the delta G between these two Is that going to be a very large numerical answer or a very small numerical answer? It's going to be a very small numerical answer. Between these two, it's going to be a very large number. So value-wise, so remember, this is not talking about positive or negative. This could be positive or negative. Same thing, positive or negative. I'm referring to the numerical value. This is a small number. This is a big number. Okay? So knowing that fact, let's go ahead and see if we are correct. So if I plug everything in here, my K value here was about 4.5. And this K value here was about 7 times 10 to the 24. So there's a big difference between these two. This number is much more larger. It's 138.2 kilojoules. The number down here, the difference between these two is very, very small. So that gives me this value right here. Okay, any questions? Now in both scenarios, Q is less than K. So they both shift to the right. So they are both considered negative. They're both considered spontaneous. Okay, any questions? All right, did anyone not understand what we just did?
Well, Professor, I just have one quick question. That's ln as in natural logarithm, correct?
Yep, natural logarithm.
Okay, I just wanted to make sure I was writing that down correctly.
Okay,
Okay, thank you.
all right. So I want you to go ahead and give this a try. This is a question that I created. It is the synthesis, well, not this part's something that people know. It's a synthesis of ammonia, but the information down here, use this information, plug it in, and tell me whether or not this reaction will shift to reach equilibrium. Will it shift to the right or left? In order to do that, you need to go ahead and calculate delta G here. You need to look at the relationship between Q and K for each one of these. Okay? I'll give you about 2 minutes to give it a try, and then we'll go over it. Okay, does anyone else still need more time with this? Okay, so let's go ahead and just plug in our first one right here. I want you to plug all of this in and tell me what you get as a Q value. Just the Q value. I'm assuming everyone remembers how to go ahead and calculate Q given a set number of concentrations or pressures. Okay, keep working on it then. I'll give you a little more time and then come back with a value for Q. While you're at it, given this information right here, I want you to also find the value of K. So that might make things a little easier for you. Okay, did anyone figure out our value for Q? You will need to figure this out in order to move forward. So it is 6.85 times 10 to the fifth power. Okay, so we'll just keep it short. 6.8 times 10 to the 5. That is about what you should have gotten. Remember, this is your products over your reactants, assuming you plugged all these into the right location. Okay, so with that said, let's go ahead and write out my entire equation. If I'm solving for delta G here, it is delta G equal to delta G at standard state plus RT ln of Q. Okay, I can replace Q. I put 6.8 times 10 to the 5, plug that in there. My R I know, temperature I know because it happens to be 298, so I can just plug that in. Okay. Perhaps we have to go back to the Q value, okay? Remember, this is products, so NH3 squared over your reactants. Okay, let's plug in our numbers now. NH3 is this one right here. So this is 2 squared. Okay. Then I have 5.84 down here. And then I have 1.0 times 10 to the negative 2, and this is cubed. Does that answer your question? Okay, it's all right. So now that we have all this, we got 6.8 times 10 to the sorry, not to the negative, 6.8 times 10 to the 5. I plug it into my equation. So once again, I have here my delta G is equal to delta G at standard state plus RT ln of 6.8 times 10 to the fifth power. Okay. My R here happens to be 8.314. And then this happens to be 298 Kelvin. When I multiply all of this together, if I did a rough estimate, this comes out to about positive 33.3 kilojoules. Okay. Does that make sense so far? Again, this is a rough estimate. It comes out to about that number. Any questions? So with that said, 33.3 kilojoules, my delta G at standard state is negative 33.3 kilojoules. So what is my delta G equal to? It happens to be equal to 0. Okay. When delta G is equal to 0, what does that tell me? You're at equilibrium. When we're at equilibrium, this doesn't shift. There is no shift because it is at equilibrium. Okay. What about my second one right here? What can you tell me about the value of Q? It is equal to 1 because this is all 1 right here. In fact, this means that if the Q is equal to 1, what do I know about delta G? Delta G is if Q is equal to 1, what can I say about delta G? It is equal to that, but you're missing a sign. It's equal to the negative RT ln K, also known as what? Standard state. So delta G at standard state. So this is what it essentially equals to because Q is equal to 1. So we get rid of that entire side. This is just this, and this is just that. Okay. Now, if this is itself, so delta G is the delta G at standard state, that is a negative here. So which way will this reaction shift? For B.
The shifting forward reaction.
So shifting the forward reaction, so to the right. Okay. Now, another way you can go ahead and do this double check, if you didn't understand or you didn't like to use this equation as much, we could essentially skip all of delta G if you wanted to for this equation, with the exception of one equation. So I go ahead and do delta G 0 is equal to negative RT ln K. I want to algebraically solve for K. K should give you a value of 6.8 times 10 to the fifth power. Now, if you had solved that, then you go ahead and just plug in your value of Q here. This Q was equal to that K. Then they are essentially delta G is equal to 0. This Q is essentially equal to 1. So it is less than that number. So it shifts to the right. So they all meet that same condition. All right. Any questions before we continue? Okay. So I'm giving you this information right here on the screen. I want you to go ahead and calculate the equilibrium constant. So I want you to go ahead and assume that you need a couple of equations. This is going to involve anywhere between 2 or 3 equations, depending on how you do this. Okay. My hint for you is that you will deal with delta G at standard state, and you will deal with this equation right here. This is how you're going to find the equilibrium constant for this K right here. Now, to get delta G, you notice they don't mention it anywhere here, but they give you delta H and delta S. What equation can I use to solve for delta G? So I have delta H minus T delta S, okay? And we're gonna assume since that is at standard state, these are all at standard state. Usually it's referring to the reaction in most cases. Now, how do I find delta H and delta S? What do I need to do? What does the delta stand for? The difference, right? So I need to take these numbers and I need to find the sum of my products minus my reactants. Okay, the sum of my products minus the sum of my reactants will give me what I need in terms of the value for delta H. Same for delta S. So I'll give you a second, give this a try, start the setup, and then we'll go over it together. Okay, so I'm going to go ahead and switch over to a whiteboard for this one. It's going to take a little bit of work to do. So does anyone still need time to copy down the question or anything from the question? We won't be able to go back to it as easily. Okay. So hopefully everyone can see the whiteboard. We're going to go ahead and get started. It's going to take a little bit of writing. Okay. We have our three equations that we did. I'm not going to rewrite them. I assume you know them already. So to find my delta H, the first thing I want to do is I want to go ahead and put this as your products minus your reactants. So the difference between the two. Okay. And remember, you need to account for the coefficient. So that big 2 that we have in front of Fe2O3 is going to be there. The number I have here is negative 826. So I'm going to plug that in. Okay. I am subtracting this by the coefficient of 3, but luckily this value is 0. So it's essentially subtracting by 0. Then I do it again. 4 for my coefficients. This happens to be 0. Okay. All of that added together, I should end up with negative 1.652. Oh, sorry, miswrote 1. Times 10 to the 6 joules. Or if I want to change it to kilojoules, this becomes 10 to the 3. Any questions? Okay. So I'm going to keep this in joules for the time being. Okay. I'm going to jump to the next page and we're going to do this again. This time I'm going to do this for delta S. Okay. So bear with me as we go through this. Again, same format. This is my 2 for the Fe2O3. And the number that happens to be 90. Okay. So this is my product. I'm going to subtract it from the next one. This happens to be my O2. And the number was 205. And then I subtract it again, this time 4 minus 27. Or 4 times 27. Now, when you do this, if you notice, you could essentially do this. You can put these together and put all of your reactants together, then subtract them. Or you can subtract it, then subtract it, whichever method you prefer. Okay, any questions up to this step so far? No questions? So you should end up with a delta S value of negative 543 joules per Kelvin. So I'm gonna go to the next page again. Now I'm gonna write in my values of delta H and delta S here. This happens to be negative 1.652 times 10 to the 6 joules. And this happens to be negative 543 joules per Kelvin. Okay. And since they're both joules now, it makes it easier. I don't have to convert them from anything else. So I'm going to go ahead and solve for my delta G. This is essentially the same value that I just wrote here, minus whatever my temperature was. I believe my temperature said it was 25 degrees Celsius, so we'll say 298 Kelvin. Right? Times the negative 543 joules per Kelvin. So once I solve for all this, my delta G should give me a value of negative 1.490 times 10 to the 6 joules. Okay. Any questions so far? Anyone confused on how I got to this step? All right. So the next part we do with this is just we're going to change this into the equilibrium constant. So my delta G, we're going to say this is at standard state is equal to negative RT ln K. Okay. We know my R value. I know my T value. This is my negative 1.49 times 10 to the 6. I plug in all my numbers. I'm going to go ahead and algebraically move everything to the other side so that this becomes negative RT on this side is equal to ln of K. So once again, ln of K is equal to negative delta G at standard state over RT. Negatives we pull out to the side, okay? This should give me a number that is 601 when you plug it in. So remember that ln of K, right? If this is equal to 601, we can solve for K by saying that this is equal to the E of 601. Any questions up to this step here? Remember the ln is related to our E here. No questions? So delta G, why is delta G itself negative? Or why is this negative here? Which one are you asking? The delta G symbol? Okay, the reason why it is negative because you have a negative right here. So let me go ahead and just erase this to make it a little more neater and change the color. So delta G at standard state is equal to negative RT ln K. This negative travels with it. I move that to the other side. So this is just essentially I bring the negative to the outside, delta G at standard state over RT. Okay. Okay. So with that said, if you get to this part right here, if you tried entering this into your calculator, you would not get a number. It would tell you error. The number you should be getting is 1.0256 times 10 to the 261. So in terms of your calculator, this will not show up. This will show up. So if you enter this into your calculator, you will get credit for it. Or if the question is asking that and you enter that in, you will get credit for it. Does that make sense so far? All right. Also, we see that this number is very, very large. Remember, our problem here was originally about the rusting of iron. So is this going to be considered favorable or not? So rusting of iron is very favorable. It happens very, very often. Okay, so it drives the reaction fully forward. It's a very favorable situation. All right, anyone have any questions? I can say yes. This one and the previous one. So if you looked at it, it's a question that involves all the equation that you had to know for this chapter, plus your knowledge of equilibrium. And that's pretty much the same for all situations from chapter 17 and onwards. It always involves some form of equilibrium somewhere in the chapter. Any other questions before we continue? All right. So some ending reminders that you want to write down. Make sure you know those laws of thermodynamics. Which one of these essentially causes us to have a spontaneous reaction? And what do all spontaneous reactions have in common? What do they all aim for? Okay. Remember the different factors that affect our entropy, or in other words, our delta S. Remember that free energy is related to equilibrium. So delta G is related to Q and K. And we can determine our delta G also through delta S and delta H. Okay. Those are our equation-based stuff. Everything else is concept-based. So at the very end, we did a bunch of equations in math, but everything else is based on the concepts. And then remember that a non-spontaneous reaction requires constant input of energy. So only spontaneous reactions will move forward once you begin it. Okay, does anyone else still need time to copy this down? All right. So a question for everyone here, what is energy made of? What two things?
Heat
Say it again.
and heat.
Heat, and what else? Something that you might have learned in physics.
Also an electron.
Not an electron.
Or
Work.
oh,
So heat and work, okay? So heat plus work. So if you're doing your homework, your Alex homework, makes you sweat, you're doing it right. Okay, so we're gonna go ahead and get started with the next chapter. Give me 1 second. Okay, just a quick check. Can everyone see the screen clearly?
yeah.
All right. So give you a second, get settled in, and then we're going to get started with chapter 21. This is essentially our last chapter that we're going to focus on. And then after that, it's just going to be review for the ACS or for the final exam. Okay, anyone have any questions before we begin?
Professor, the final exam is going to be in person.
Yes, as far as I was aware, that's the only one in person.
And this is going to be when?
I have to double check the date, but it's either going to be the 14th or the 21st, whichever day we actually have for that final. Because I think they were a little confused with the scheduling, so I was a little confused as well. So once I get a final answer, I will tell you which day. It's either going to be the 14th or the 21st, whichever that Tuesday is.
Of December, right?
Yes, of December. Not
Okay.
next week. Don't worry.
Just wanted to make sure that, because I was about to say.
Let me check my schedule real quick.
All right, thank
December 14 or December 21st. Okay. In terms of whether it's going to be a state exam or the class final, as far as I was told, that more than likely it's going to be the ACS supplied by the department. Now, if something changes, I do have a final ready in case that is the case. All right, so let's get started. Yes, all multiple choice, about 70 questions. You have about your 2 hours to complete it.
If it's the 14 or 22nd for final exam, what time for final exam?
I don't know when it is. It's either the 14th or the 21st of December. I don't know which of those days, but it's always going to start at 4 o'clock. Yes, we will have a review as we finish this. If you look at it, we're on chapter 21. When we finish chapter 21, we will begin our review. Yes, in person. Again, whichever day they give the final, because I'm not sure if they scheduled Tuesdays for the 21st or the 14th as the week of the final. So they were unclear about it at first. So I'm going to check with them again. Okay. In my opinion, my final exam and the ACS final, I find easy, but that's my personal opinion. Easier than my quizzes. Okay. In terms of review sheet, I'm sure you can make your own review sheet as well. That's probably more beneficial for you to create your own review sheets. All right, so for chapter 21, electrochemistry, How many of you have heard of redox reaction before?
I have.
Okay. I will be printing out not a reference table for you. Reference table is usually for high school. There will be just a data sheet with the periodic table on it and some equations. That is usually provided with the ACS final exam. Okay, so a little bit about redox reactions. We have two parts. It's made up of two names, oxidation and reduction. Okay. You will get that the day of, along with the final exam booklet. So oxidation is the loss of electrons, reduction is the gain of electrons. So they're always referring to the oxidation number. That's why it says reduction. Because when you receive electrons which are negative, your oxidation number goes down. So it is being reduced. And these two things happen at the same time. Something is always going to receive those electrons and something is always going to give those electrons away. And just as I mentioned, oxidation is the result of increase in the oxidation number. Reduction is the decrease in the oxidation number. Now, this is the part where a lot of students get confused. So I want to emphasize this. This part right here, okay? The oxidizing agent is what causes something to undergo oxidation. It causes something to undergo oxidation. So the agent itself is not undergoing oxidation. It causes something else to undergo that. How many of you have heard of 007? Or James Bond? Or secret agent, right? So the agent is someone that causes something to happen, okay? They're not the one that undergoes the thing. They are causing someone else to undergo something. So if I looked at a spy, for example, they're spying on someone else. They're not the ones being spied on. Does that make sense? I'll take your silence as a yes then. So once again, the oxidizing agent is the one that causes something else to undergo oxidation. It itself is undergoing reduction, okay? The reducing agent is causing something else to undergo reduction. That means it itself is undergoing oxidation. So I want you to remember this term. If you see the word agent, it doesn't mean that this is undergoing the stuff. It is causing something else to undergo it. All right. So let's take a look at the example here. We look at the before and the after. This arrow is telling us it's going to the right. You start with a charge of 0. Anything that is just the solid form or the atom itself usually has a charge of 0. So this is a neutral atom. This essentially becomes +2, okay? And this +1 becomes 0. So the number of electrons being transferred should always be the same, and it matches up because this tells me that this essentially has lost 2 electrons in the process. So zinc has lost 2 electrons, so it goes from 0 to +2. Here there are 2 of these H's. They're each +1. They've both each one of them has gained 1 electron, so that's why the overall charge becomes 0. Does that make sense to everyone so far? Okay. So once again, zinc here, the oxidation number is increasing, so that's undergoing oxidation. Hydrogen is undergoing the reduction. In terms of reducing agent and oxidizing agent, zinc is the reducing agent. It is causing hydrogen to undergo reduction. It itself is undergoing oxidation. And then hydrogen here, oh, I guess it didn't show. Hydrogen here is undergoing reduction, so it is the oxidizing agent. Okay, any questions? All right, let's continue. We have a method of essentially determining oxidation numbers. So some of you might have learned how to assign oxidation numbers back in Chem 1, I'm assuming. You might have or you might not have. Does anybody remember that? Okay, guess not. Maybe some of you did, or maybe back in high school, you learned some rules about assigning oxidation numbers, where hydrogen was +1, group 1 is always +1, oxygen is -2 or -1, depending on the situation, things like that, okay? So we could do that as well. We could go with assigning oxidation numbers, remembering all those rules. The other method that we can do is called the half reaction method. So we kind of split this into your oxidation and reduction. We do all of the balancing for this, and then that will essentially figure out what our oxidation number is for every single thing without having to assign it randomly on our own. Okay, so there's going to be a lot to follow through with this one. Bear with me as we do this because this is going to be very, very detailed. Okay, it's going to be a lot of steps. So we have two types. We're going to deal with the acidic and basic solutions. Basic solutions we'll worry about afterwards. It is acidic solutions plus a few more steps. So it's acidic plus essentially. Okay, first one. You want to separate this into your half reaction. One piece is going to be oxidation, one piece is going to be reduction. Even if you don't know which one is which, that's perfectly fine. You just separate it based on the types of species that are there, okay? The next thing you're going to do is you are going to balance all the atoms and charges of each half reaction. The number one thing you want to balance first is any atom that is not oxygen and hydrogen. So you balance those atoms first. So if I have chlorine and then Cl2, I want to make sure that I have the same number of chlorines on both sides. Okay? With that said, once you have balanced those atoms, you then balance oxygen. And the way you balance oxygen is usually with water. Then you balance hydrogen, usually with hydronium charges or H+ charges. After that, you balance the charges. You can only add electrons in this scenario. You can't add any positives, you can only add negatives. So you want to make sure both sides have the same charge. Okay, once we're done with that, sometimes one side has X many electrons, the other side has maybe twice as many or less, right? You need to make sure that both sides, if I put in 5 electrons, I should get 5 electrons out. So then we're going to go ahead and multiply the entire half reaction by an integer to see if the number of electrons gained is equal to the number of electrons lost. So it's like if I hand you $5, you should be receiving $5. If I hand you $5 and you only receive $1, something is wrong with that math. So we're keeping the same exact concept in terms of electrons. Electron gained equals electron lost. Now, if none of this makes sense to you, it's okay because we're going to do some steps and go through it one at a time. All right. And the last thing you want to do, you want to put your two half reactions back together, include any states of matter, and then cancel out anything that shows up on both sides, the left and the right. And then essentially we have done the half reaction method and balanced our entire equation. Anyone have any questions? Okay. So we're going to go ahead and try this with an acidic solution. This is our equation given to us. If you look, even just looking at the equation, we can see that this is not balanced. On the left side, I have 2 chromiums. Here I have 1 chromium. Things don't make sense. Okay. So using the same steps that we just talked about, we're going to do this one step at a time. The very first step, divide into half reactions. The best way to look at this is this has chromium in it, this is chromium in it, this is iodine, iodine. So these two go together, these two go together. Okay. Now, whether or not I know this is going to undergo oxidation or reduction, that I can't guarantee you of yet. But I do know that these two go together, these two go together. And it's usually split right down in the middle, one from the left side, one from the right, one from the left, one from the right. All right. Anyone have any questions up to this point? Okay. So these are my two half reactions. I'm going to go ahead and balance my half reactions. First thing I want to balance is anything that is not oxygen or hydrogen. If I look here, there's 2 chromiums here, then I need to put a 2 in front. So I can only add coefficients. I can't put a 2 like this. It doesn't work like that. Okay, anytime you're balancing things, going back to stoichiometry, you put the coefficient in the front. So you put a 2 here to indicate that there's 2 chromiums, 2 chromiums. All right, any questions up to this step? The next thing I want to do is I want to balance the oxygen. And the way I balance oxygen is I must add water. So I'm going to add 7 waters because each one of these gives me 1 oxygen. So 1 water is 1 oxygen. I need 7 of them because there's 7 here on the left side. Okay. So I add 7 H2 on the right. Now I've balanced the number of oxygens on both sides. All right. Does anyone need time to copy this down before I move forward? It is a lot to write down, just so you know. Okay. So the next thing I want to do is I want to balance the hydrogens. So if you look carefully here, this has my H2O. So 7 times 2 gives me 14 hydrogens. I need to account for those 14 hydrogens. The way I can do that is by adding H+. So we're under the assumption that this is an acidic solution, so I can add any amount of H+ that I choose, as long as it balances the equation. I'm gonna add 14 to the left side to match the 14 here. So as of this step right here, above this line, I have balanced my atoms. If I have five carbons, I should have 5 carbons on the other side. If I have 10 hydrogens on the left, I should have 10 hydrogens on the right. Same thing with oxygens and any other atom that I have. Okay, any questions up to this part? All right, with that said, now I want to look at the charge. Okay, so if I look at the charge on the very top here, I have here -2 from the chromium, right? This is the -2. On the right side here, I have 2 times +3. So this comes out to +6 on the right side. So this is +6, okay? Let me rewrite that so you see it. This is +6 on the right side as an overall charge. On the left side, I have a -2 here, but I also have +14. So on my left side here, if I look at the total amount here, it becomes +12. So which side is more positive, the left side or the right side? Not a trick question. The left side, right? So remember, I can only add electrons. So which side would I add the electrons to, left or right? Remember, electrons are negative. I'm going to add it to the left side. I'm adding this in here. Remember, electrons are negative. So by the time this is done, this becomes +6 now. So they now both match. Okay, any questions in that first part? This is just one of our half reactions. We have the other half to deal with. Now, a way we can also double check this is if you wanted to just go ahead and look at what the oxidation number is for this, the overall thing should come out to -2, right? Each one of these oxygen is -2. So that's a total of -14. This is our -2. So this should be 12 that's missing. So this should be +12. So there's 2 of them. This is +6 for the chromium. So it goes from +6 for the chromium to +3. So this is undergoing reduction. Another way we can look at this is if you're adding the electrons to the left side of the equation, you are trying to reduce that thing. If the electrons are coming out on the right side of the equation, it's undergoing oxidation. So this is undergoing reduction because you're adding electrons to the left side. You're adding it into the equation. Okay. With that said, let's go look at their other half of the half reaction. Again, I put a 2 here to make sure that both sides have the same number of iodines. I have no oxygens or hydrogens, makes it easy. I just need to balance the charge. This is now -2 on the left side. And this charge on the right is 0. Remember, I always add to the side that is more positive. I add electrons to the side that is more positive. If I add 2 electrons here, this now becomes -2, -2. Okay, any questions on that? All right, with that said, let's put our 2 half reactions next to each other. My chromium one has 6 electrons in terms of movement. My iodine only has 2 electrons. So I need to multiply it by 3, the entire equation, so that now it also produces 6 electrons. So 6 electrons going in means 6 electrons coming out. Any questions up to that part? Okay. So when I add them together, I put everything on the left side, everything on the right side. Anything that shows from both sides to cancel out happens to be just the electrons. Sometimes you need to cancel out some water, sometimes you need to cancel out some H+. But it shows up on both sides here. Oh, sorry, it doesn't show up on both sides, so you're good to go. 14 here and 7 here. This is my entire equation now. Anything that has a charge to it, right? Anything that's an ion, you write aqueous. Water, you put it as liquid. The original one, if it was solid, you keep it as solid. Okay? And this is essentially how we go ahead and balance using the half reaction method to find acidic solutions. Any questions as of now? Okay. So the other thing that you're going to do in terms of basic solutions is you do everything you did for the acidic solution steps. You got to where you were. So you should be getting to exactly this spot right here. Okay. The only other difference is when you're dealing with basic solution, you do the same stuff. Now you need to add OH ions in. So before in a previous one, we had 14H+ on the left. Sure. This one? Okay. Yeah, you wouldn't, well, the only reason that you would be able to can't join them together in the first place, right, is if the electrons are equal. So remember how the electrons were not equal in this scenario right here, right? I need to go ahead and multiply this by the integer so that now both sides have the same number of electrons. Then you can cancel it out. You should have no electrons shown in this bottom part here. Okay, if there's electrons shown, that means you didn't do your balancing or calculation correctly. You go back and redo it. You can have any number of H plus, you can have any number of waters or anything else in charges. You just cannot have electrons hanging on the left side or right side. Those should be completely crossed out or cleaned out when you combine the equation back together. Okay. Now with that said, whichever side has H plus ions on it, right? For after you finish your acidic solution, you add OH minus. You add that many OH minus so that you can make water. Okay, if this was 7, you put 7 of these. So it's 10, you put 10 of these. If it was 5, you put 5 of those. But the thing about this is now this is one entire equation. So if you add 7 OHs to the left, you must add 7 OHs to the right. So you must add to both sides now. And remember, as I mentioned, any H plus and OH minus that joins together makes water. You should have some water on one of the sides. So you should have to cancel out some of the waters. So that is essentially a basic solution. You do this on top of the acidic solution, you add in OH and then change it to water, cancel out any waters on both sides. And so now your equation should have some amount of OH in it and less water if you canceled out some. Okay. Anyone need time to copy anything from this page here before we move forward? Okay. So why don't we try this? I'm going to have you practice some acidic solution steps. So copy down these two, and we're going to give these two a try, and then we'll go forward from there. Okay, just a quick check. Does anyone else still need time to copy down the equation? Just copying it down. All right, so we're going to switch over to the whiteboard because this is going to require a lot of typing or a lot of writing. Okay, so let's do the very first one. I have here I negative, right? Plus CLO minus changes into I3 minus, and then I have CL minus. So I'm not going to write the phases just because I'm saving some time on this one. So I know the I's go together, the CL's go together. So I have I minus, I3 minus, and then I have CLO minus, and then CL minus. So I'm splitting it like this. Okay. Any questions so far? All right, with that said, what can I put in front of this I to make sure that both sides have the same number of iodines? I can put a 3. Okay, so I'm just going to draw it up here if you can see the difference. So this is a 3 now. I don't have any oxygens or hydrogens. I can skip that part. The next thing I want to do is I want to balance the charges. What is my charge on the left? I'm just going to write the number here. My overall charge on the left side. I'll give you a hint. It's a negative. It is -3. What's my overall charge on the right? -1. So which side am I adding electrons to and how many? I'm going to add electrons to the right side, actually. Remember, electrons are negative. I'm going to add 2 negatives to the right so that this becomes equal to -3. So this new number becomes -3. Does that make sense? All right. So let me just go ahead and rewrite that so it's a little neater on the very bottom. I have 3I minus changes into I3 minus plus 2 electrons. This is telling me that everything is balanced here, okay? I have the same charge on both sides, the same number of ions on both sides. I'm going to leave this here for now, and now let's go focus on the right side. So on the right side now, if I look at the number of chlorines, do I have the same number of chlorines? Yes or no? Yes, right? So I don't need to do anything. The next thing I do is focus on the oxygen. Over here, since this is an oxygen on the left, I can do 1 water on the right. So now the oxygens are balanced. And then now I have to balance the hydrogens. Since water here gives me 2 hydrogens, I need to add 2 hydrogens on the left, 2 H pluses. Okay, with that said, I have now balanced all of my atoms. Okay, I need to balance my charge. So tell me, what is the charge on the left side in total? My overall charge on the left. It is +1. What's my overall charge on the right? Okay, how many electrons do I need to add and to which side? I add 2 electrons to the left side here. And so now my overall charge here becomes -1. Okay. Now let me rewrite the entire equation with all the information we have. So I have ClO minus plus 2 electrons, right? Changes into also 2 hydrogens. So 2H plus ClO minus plus 2 electrons is equal to ClO minus plus H2O. Now looking at these 2 equations, it shows me that I have 2 electrons being lost here, 2 electrons being gained. This is on the left side of the arrow, right side of the arrow. Why did I add H plus, 2 of them? Because this has 2 hydrogens. I need to account for those 2 hydrogens. Does that answer your question? Okay. So 2 electrons on the left side, 2 electrons on the right, they are essentially equal to each other. So now I can add the 2 equations together, okay? I'm going to erase this top part when you use the space right here, just so I can keep it all on the same page. So I'm going to put everything that is on the left side, everything on the right side. So I have here 3I minus, and then I have 2H plus. I'm going to skip right in the electrons as we go through this because we don't need to include the electrons because we assume that they cancel out. So this is going to cancel out on both sides. Now on the right side, it is I3 minus Cl minus plus H2O. Right? We didn't leave anything out. We used all the pieces. Yeah. Okay. So this is my equation. To finalize this, anything that has an ion form is an aqueous solution. Okay. And then anything that is water is liquid. So this is aqueous, 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 aqueous. All right. Any questions? Okay. So with that said, let's go ahead and try the next one. Do you want me to let you try this one on your own, or do you want me to go through it as well? Or how many of you actually finished it already? All right, give it a try, and then we'll answer it on the screen here, okay? So I can't really go back to the second reaction because that requires switching the screen completely. I would rather keep this up. So if someone wants to go ahead and just type what the second reaction is, you can see it on the screen there. Okay, so let's go ahead and begin. I'm going to separate this into the half reactions. I have As2O3 on this side, and then I have H3AsO4. Okay, and then on the right side is NO3 minus, and then NO. Okay, let's focus on the left side first. If I look carefully at this, I have 2 arsenics and 1 arsenic here. Okay, so I want to go ahead and double this value right here. So now the same number of arsenic shows up on both sides. Okay, so now I have 8 oxygens on the right, 3 oxygens on the left. What do I add and how many and to which side?
Professor, don't you do 4 oxygens on the left side?
Not
So
4,
it'd be
5. Remember, there's 8 on the right here. This is 3.
oh no, because I was gonna say because oh wait, no, you're right. Never mind. I see.
Okay.
Oh yeah, because we're using H2O.
All right. With that said, right now I have the same number of oxygens and arsenic on both sides. What do I add next and to which side? How many hydrogens do I have on the left? I have 10 hydrogens, right? On the right side, I have 6 hydrogens, the 2 times the 3. So I need to add 4 more hydrogens on this side. Okay, any questions up to this step here?
Professor, why can't we have to add specifically water then for these equations either way then, right?
Yes.
Okay, thank you.
All right. So now we should be balanced on both sides in terms of atoms. What is the last thing I need to add? And to which side?
The electron.
Okay, how many electrons and to which side?
Would it be 1 electron to the right?
Not correct. How many of these positives do I have on the right?
You need 4 electrons to the left.
4 electrons to
it's
the
not-
right side.
To the left, to the right, my bad.
Okay.
Mhm.
So 4 electrons to the right side. Now I want to put all of this together. I'm going to leave this here just to save some space. I'm not going to write it in yet. Okay. Let's focus on the right side. So do I need to change the number of nitrogens?
No,
No, right? I focus on oxygens next. How many oxygens do I add and to which side? Or how many waters do I add?
you add 2 waters to the right.
Okay. What do I do next?
You add 1 hydrogen to the left,
Not 1,
or 2 hydrogen.
not 2,
4.
4 hydrogens to the left. Okay, this is 2 times 2. That's what these two things mean. So in total, I should have 4 hydrogens on the left. Now, how many electrons do I add and to which side?
Is it 3 electrons to the left because there's already a negative?
That is correct. 3 electrons to the left, not 4. See the negative here, canceled out one of them. So now the total charge on the left is 0. The total charge on the right is 0. Okay, it works out for us because they both sides have total charges of 0. Okay. Now, with that said, I would put the entire equation together, everything on the left, everything on the right. Before I do that, just to make my life easier, we can see that the number of electrons on both sides do not match, right? So this entire thing is put in a bracket. What do I multiply this side by and what do I multiply this side by to make sure the same number of electrons are on both sides?
4 over 3 and 3 over 4.
I multiply this by 3 and multiply this by 4. Okay. Now go ahead and do that and then write in your final information on the bottom, or I'll write on the next page. So I'll give you a second to copy down whatever you need, do the multiplication, write in everything on the left, everything on the right, or write the half reactions if you want to do that first. But this is going to take some time to write down. I'll give you some time to write it down on your own as I start writing it here. Okay. My mistake. That's a 4. Okay, so this is what you should have ended up with. What can I do based on this information? What can I cancel out?
Can you cancel out the electrons?
The electrons are canceled out. Okay. So that's out of the way. What else?
I don't think anything else can.
You can cancel out more stuff. You can cancel out the water, right? This has 8, so I remove all 8. This one I change the number to 7. Okay, since there are 8 on both sides, I remove those 8. What else can I cancel out? The H plus. I remove all of these. I change that number to 4. Okay, does this make sense to everyone so far?
Yeah.
All right. So now at this point, you just simply put in whatever the original states were, or the states of matter. No, I did not do that yet. So I want to bring up that I'm not going to do the poll for today. So we're going to end actually right here after this one. You will go ahead and, well, actually, I didn't show you the two yet. So give me 1 second. Does anyone need to copy down the screen before I clear it?
I'm copying it down right now.
Okay. To give you some time to copy it down. There is no poll for today. We will end on this slide here. Okay. The next time we come back, we will start talking about the basic solutions and go forward from there. Anyone
Okay,
have any
and-
questions?
Well, yeah, Professor. So this whole part of the chapter is just writing these equations to see, to just to get them
balance
equal
it.
to each other. Yeah, to balance it. Okay.
And to figure out which one's oxidation, which one's reduction, how many electrons are being transferred.
Oh, so this is basically like expanding even further on like the definitions of them from like last semester in 113.
So this is stoichiometry, this is redox reactions, this is balancing equations, and this is why I added 4 electrons and 3 electrons. So the reason why I'm adding 4 electrons is because this overall charge on this side is 0. The overall charge on this side, because of these, is +4. I add electrons to cancel out and make that 0. On the right side here, charge is 0. On this one right here, this is -1 plus 4, +4 gives me 3 positive. So I add 3 electrons to cancel that out and make it 0. Does that answer your question? Okay. All right. Does anyone else need time to copy this down? Okay, so we're going to go ahead and end it here. For the co-host, you can go ahead and stop the recording. Does anyone else have any questions? Okay, so we're going to transition into the office hours. Yes, the reducing agent is the one being oxidized. Okay, so we're going to transition to office hours, maybe give or take 6:30 around then. So if you're going to join for office hours, come in during that time. Other than that, enjoy your day. I will see you all next week. And there was no poll question this week. So as long as you attended, it shows up that you did it. Okay, I give you full credit for it. Okay, any last minute questions before I go ahead and close out the session? Yes, next week we're continuing with chapter 21. Okay, if there are no other questions, I'm going to go ahead and close everything here. All right.